This is section 9.7, circles and lengths of segments. So we now know how to find the measure of pretty much any angle that's formed by chords, secants, or tangents. So you know how to find it if it's a central angle or if it's an inscribed angle. Last section we saw how to find it if it's just any two chords, where we have an angle inside the circle. If it's an angle formed by secants and tangents where the vertex is outside the circle, we know how to find that as well. But how do we find the lengths of the chords, secants, and tangents themselves? Not the angles that they form, but the actual lengths of the segments. Like in this picture, I've got two chords, A, B, and C, D, and they intersect inside the circle at point P. Notice neither one of those chords goes to the center, so neither one of them is a diameter. So how am I going to find R, S, T, and U? Let's try to find a relationship between those four segments. Those segments are called segments of the chords because they're formed by the intersection of chords. Let's try to figure it out. It would be most helpful if we could give ourselves some shapes to work with. The shapes that I'm going to draw here are just formed by connecting A and D and C and B, giving me two triangles, triangle ADP and triangle CPB. Well, I know some things about these triangles. For instance, I know that I've got a pair of vertical angles in the middle here at point P. So that gives me one pair of congruent angles. Angle APD is congruent to angle BPC because vertical angles are congruent. That's nice. Do I know anything else about these triangles? There's no parallel lines, so I don't have any kind of alternate interior angles or anything like that. But these are inside of a circle, so we must have to use that. Well, angle ADC, this angle up here, that's an inscribed angle, and its measure is going to be half the measure of arc AC. But angle ABC is also an inscribed angle, whose measure is also half the measure of arc AC. Well, that's nice, because if that's true, then I've got two angles that are congruent. Angle D is congruent to angle B. They are inscribed in the same arc. So they're congruent because they're both half of arc AC. That gives me two angles within those triangles that are congruent. Well, that's nice, because if I have two angles within two triangles that are congruent, two pairs of angles, then those two triangles themselves are similar. So triangle ADP is similar to triangle, I have to be careful about how I name these, CBP. ADP, CBP. Why are those similar? Angle similarity. Well, that's nice. Why does it matter that I have two pairs, that I have a pair of similar triangles? I was interested in the segments. Well, what do the similar triangles allow me to say about these segments? They allow me to make a proportion where R corresponds with T, so R over T equals U over S, because corresponding sides of similar triangles are in proportion. So that means, I'm done with the picture here, that I can cross multiply and say R times S equals T times U. What allows me to cross multiply, this is the property of proportions. This equation, this relationship, is exactly the conclusion of our first theorem. And what this is saying is that if I take R times S, the two segments of one chord, and I multiply them together, I'm going to equal the product of the two segments of the other chord, T times U. So that's this theorem. When two chords intersect inside a circle, the product of the segments of one chord equals the product of the segments of the other chord. Two chords are intersecting inside my circle. AB intersects CD at point P. The product of the segments of one chord, R times S, equals the product of the segments of the other chord, T times U. It's a nice relationship. So if I know three of them, I can find the fourth one just by solving the equation. What about this scenario? Here we don't have chords, we have two secants. Well, we do have chords, A, B, and C are chords, but we've extended them and we have secants because those chords don't intersect inside the circle. So we can't apply the first theorem. But those secants do intersect at point P. Turns out we could form similar triangles here by drawing AD and BC. This time our similar triangles are ADP and CBP. Those turn out to be similar triangles, and so we can set up a similar relationship as before. So when two secant segments are drawn to a circle from an external point, the product of one secant segment and its external segment equals the product of the other secant segment and its external segment. A lot of words to express a fairly simple idea. So when we say the product of one secant segment and its external segment, we're referring to, say, R is a secant segment of the entire secant AP, and its external segment would be S. And then the other secant segment and its external segment would be T, the whole secant, and its external segment is U. So the product of R and S equals the product of T and U, which should look familiar because it's exactly the equation we came up with in the earlier scenario. Except this time, it's the whole segment and the outside part multiplied together equals the whole segment and the outside part multiplied together. So it's not two pieces, it's the whole thing times the outside part equals the whole thing times the outside part. Then our last situation. This time we have a secant and then a tangent. When a secant segment and a tangent segment are drawn to a circle from an external point, the product of the secant segment, R, and its external segment, S, is equal to the square of the tangent segment. It seems weird that we're all of a sudden introducing squares. It's actually not weird at all. This says R times S equals T times T, T squared. The reason for that is that this is really just an extension of this scenario. If I make CP a tangent instead of a secant, then T becomes U. T and U become the same thing. So this is really like saying T and U are equal, and I just got T times U over here, but that's T times T, which is T squared. So it's really the same relationship. That's just being extended from two secants to a secant and a tangent. So the whole secant times the outside part equals the tangent times itself, the tangent squared. So you've got this scenario. R times S equals T squared. Let's look at some examples before I set you loose. Find the values of the variables. So in number 1, I've got two chords intersecting inside of a circle. So I know if I multiply the two segments of one chord, like x times 3x, that's going to equal the product of the two segments of the other chord, 6 times 8. Okay, well, what happens when I multiply x times 3x? Is that 4x? No. It is 3x squared. 6 times 8, we know, is 48. Divide both sides by 3. Just going to tell us that x squared is 16. Which means x equals the square root of 16, which is 4. So I used the first theorem that we had today. In number 2, we've got 3 lines there. I've got two secants, the green one and the purple one, and then I've got a tangent, the yellow one. So when we're finding x, let's use the two secants. Because if I use the tangent, I'd be introducing a second variable, which is not helpful. So finding x, let's use the fact that the whole secant, 9, 5 plus 4 is 9, the whole secant times the outside part, 4, equals the whole secant, x plus 3, times the outside part, 3. Whole secant times the outside part equals the whole secant times the outside part. 9 times 4 is 36. Let's distribute the 3 over here. 3x plus 9. Subtract the 9. We'll get that 27 equals 3x. We divide both sides by 3. And x equals 9. We still have to find y. Y is a tangent. So we could use either the green secant one or the purple secant one now that we know x. Doesn't matter. Let's use the green one. So the whole secant, 9, times the outside part, 4, equals the tangent squared. 9 times 4 is 36, which is going to be y squared. That means y is the square root of 36. But the square root of 36 is 6. So y equals 6. So number 1 was an application of our first theorem today. Number 2, we used the second theorem to find x, and we used the third theorem to find y. Do the same thing on your immediate practice problems. Find the value of x. Make sure you draw the pictures and show your work. Do both, or you'll get a 0. That is the end of section 9.7.